So for number 40, we want to take the area bounded between these two curves. The hyperbola y squared minus x squared is equal to 1, and the line y is equal to 2. And we want to revolve it about the y-axis. So we're revolving it about here. Now, when we revolve this whole area in yellow about the y-axis, let's think about what's going to happen here. So if I'm going to take the right-hand side of the curve, and I'm going to revolve it, and that is going to give me a bunch of circles, right? So I'm going to revolve it here, that's going to give me a circle, revolve it here, that's going to give me a circle, and so on. But if I take the left-hand side of the curve, here, revolve it, here, revolve it, and there, we can see that we're going to end up with the same volume, right? Because there's some overlap here. If I take the right-hand side and I revolve it, that's going to overlap with the left-hand side and vice versa. So I only have to revolve one part of it, right? So that's what we're going to do. We're going to take it we're going to sum up these circles here. And we're going to sum them up from this point, which is the point 0, 1, all the way out to this point, which is 0, 2. So our volume is going to be the sum from 1 to 2 of a, y, dy. And we're summing up, it's an AY because we're summing up the areas vertically, right? We're summing them from across the y-axis from y is equal to 1 to y is equal to 2. So this is our area. This is going to be our AY, and it definitely does change as a function of y, because the further that I go along my y-axis, we can see that the bigger that my circle is going to become, right? So let's think about what this area is going to be. The area of any circle is pi times r squared, and now all we need to do is figure out a way to express the radius in terms of y. So the radius here, we can see, is wherever we touch this red curve and we revolve it, right? And so the radius is going to go from the center to wherever it touches the curve, from the center to where it touches the curve, and so on. And so it's just pi times the curve squared. However, this curve right here, it is not as a function of y. We have to make it as a function of y. So what we're going to do is we're going to isolate x so we can express it as a function of y. And so I'm going to bring the x to the other side. So x squared is equal to y squared minus 1, and therefore x is equal to plus or minus square root of y squared minus 1. And now we're only going to take the positive root, right? Because we're looking at the positive side. So we're looking at the positive part of it. If I were looking at the negative side, then I would have to calculate down here, which I could have done, but I chose instead to calculate it from the positive side because it's just easier. And so this is going to give me pi times the radius is this curve right here, so pi times square root of y squared minus 1 squared. So the root cancels out with the power, which is equal to pi times y squared minus 1. Okay. So once we have this is our AY, right? Now we can plug this into our integral. And so our volume is going to be the integral from 1 to 2 of pi goes outside because it's a constant, and that is y squared minus 1 dy. So we are ready. We just need to take the antiderivative. So that's pi outside, y cubed over 3 minus y from 1 to 2, which is equal to, let's see, pi goes outside, that's 8 over 3 minus 2, and then minus 1/3 plus 1. And so this is going to give us pi times 4/3. And so that's the volume that we get when we take this area and we revolve it about the y-axis.